So, let us now talk about hypothesis testing, which is concerned, and this is one of the most critical and core tasks of any data analysis. It does not matter whether you are doing time series modeling or machine learning or pattern recognition, whatever may be the data analysis exercise that you are looking at some point in your data analysis you would be testing some kind of a hypothesis, because the objective of any data analysis exercise, although in the beginning is exploratory, later on it becomes confirmatory. You must have heard of these two terms in data analysis. One is called exploratory data analysis, other is confirmatory data analysis. Exploratory is I do not know anything, I am just exploring the data, I want to define a problem, I want to do something with this data, right. Confirmatory is you begin with a postulate and then there is a certain objective and a direction to your data analysis. So, at some point you have to ascertain whether the postulate that you have made is confirmed, right, and again there, because of the uncertainty, you can never answer this question with 100% certainty. So, what you are doing in hypothesis testing is you are using data as an evidence. You first begin with a postulate and you search for evidence in the data. If that, what kind of evidence are you searching for? If whether this evidence is refuting the postulate that you are making. So, it is a different kind of search. You are not searching for evidence that supports your claim. Yes, in that process you may think you are doing that, but in hypothesis testing typically you make a postulate which is called the null hypothesis, which is a default one, which will hold even when the data is not given. That is, you make the claim, for example, that the mean of some process is something. It is either up to you or someone else to refute that, to show evidence that this claim does not hold. So, what does one do? Collects data and then, like a detective, searches through the data, searches for evidence to see if the null hypothesis can be refuted. If there is insufficient evidence, the benefit of doubt goes back to null hypothesis. That is exactly like you do in a court of law, where the default hypothesis is that the accused is innocent. Does not matter what has happened, to begin with the accused is always innocent, and the reason is, as we say in a court of law, at least in most judicial systems across the globe, the premise and the principle is that the innocent should not be punished even as the culprit may go scot free. Okay. So, we want to make sure that the benefit of doubt is always given to the accused. Then it is of course the lawyer who is actually trying to prove that no, the accused is not innocent. It is a burden of that lawyer to prove that, to provide sufficient evidence that will pull the judge away from that null hypothesis. So, it takes quite a bit of power, and that is why the power of a hypothesis test is actually rests on your ability to provide evidence and the method of testing, everything put together to pull the court or any data analysis exercise from the default null hypothesis, because the default is null hypothesis. So, there is always a tendency to go back on it and it is a fallback option. So, there should, that is of course when the truth is that the null hypothesis is false. So, your ability to reject the null hypothesis when it is false determines the power of the hypothesis test. Okay. What I am going to show you very quickly is a procedure for hypothesis testing, and you have to ask yourself, why on earth we are talking about this in time series modeling? Can you give me 2 examples why I should be interested in hypothesis testing in time series analysis? Whatever I teach in this course has a bearing and it is an integral part of time series analysis, but you should be convinced more than me. Where do you think these kind of problems arise in time series analysis?
Testing models.
Sorry?
Checking which model is the better one.
But what would be your hypothesis there?
Like one, okay, both models are same, and like the.
Can you translate that to a statement on parameters? What is the, let me give you a hint. See, this is where I require you to think. Learning concepts is one thing, applying them is another thing. I am sure you would have realized that in quizzes also. I would like you to think where hypothesis test occurs, and I will give you a hint. What is the first step in time series analysis in modeling? What is that? What is the technical statement? I mean, having gone out of a time series analysis course, you should use the technical terms correctly. Okay, one is stationarity, very good. So, how would you check for stationarity? Maybe one of the non-stationarities you would check is for integrating effects, and we say that an series has integrating effects if the pole is on the unit circle. So, I would fit an AR1 model and ascertain the null hypothesis that, let us say, it is the pole is not the pole is at 1, and then the alternate hypothesis, no, it is not at 1. The other standard test is, if you are given it is stationary, what is this other standard step that you would take? Yes. So, as like many of you have been saying, I want you to use the correct term. We perform what is known as a whiteness test, right. What does whiteness test translate to? This is a statement, verbal statement, but what is a statistical statement? So, the null hypothesis is that the ACF is 0 at all lags, right. So, this one, the common hypothesis that we run into is that the ACF, or you can say sigma or rho, is 0 for all lags, and the alternate is it is not for some lag. Of course, it is a tough one to test, but we will do it. The other kind of hypothesis test that you would run into is concerning modeling. You would, this whiteness test not only appears at the beginning of the time series modeling, but also post modeling, where you are testing the whiteness of residuals, right. The second hypothesis test that is commonly encountered in time series analysis is that the parameter that I have estimated in a model is 0, the true parameter. Where is that coming from? What is the verbal statement corresponding to that? If I am testing a null hypothesis of this type, what is the verbal statement? Now, I am giving you the statement. It could be that either one parameter or a bunch of parameters in the model are 0. Let us say a single parameter, and the alternative is it is not. Where does this come from? Okay, not bad, but is there a better way of putting it? The verbal statement corresponding to this is that I have over parameterized the model. I have included a parameter that was not necessary. So, these kind of hypothesis statements come about in when I am testing for overfitting, right. What does overfitting mean? That I have unnecessarily complicated the model more than what it should have been. For example, the underlying process may be AR2, I must have fit an AR3, right. This could also be applied to PACF, for example, PACF beyond a certain lag is 0. So, there are many different hypothesis tests that you would encounter, but predominantly these are the ones that you would run into, apart from the standard hypothesis test on mean being 0 or the variance being of some value and so on. But by and large you would encounter hypothesis test of this type. So, this is for whiteness. It is only appropriate I use a white chalk for this, and this is for overfitting or over parameterization. Elsewhere in spectral domain, you can have another hypothesis test, which is that is the equivalent of whiteness test in the spectral domain would be that the spectral density is equal at all frequencies. That is another hypothesis test. So, there are number of hypothesis tests, and you should go back and think as to what are the different kinds of hypotheses. Just go through that exercise. You do not have to do it manually. That is, you do not have to simulate something and do it, but think, go through that thought process, and believe me, you will learn a lot more than you would just by listening to the lectures. So, the first step in hypothesis testing is to formulate the null hypothesis. Second is to choose an appropriate statistic. As I said, like a detective, you go and investigate, find out if there is evidence, and the statistic is like your lens. And then the first step is very, very important. You have to formulate the right null hypothesis and the alternative one. And the third step is to compute the test statistic from the given observation. And fourth one is to make a decision whether what you have observed conforms to the null hypothesis or against it. That is what we mean by make a decision. And at that stage, in fact, when you are computing the test statistic, there is a very important point there, which is that you hold on to the null hypothesis. You assume, until you make a decision, you assume that the null hypothesis is true. Then you compute the statistic. For example, here you would compute this statistic, right. So, here it would be sigma of the process. Suppose I am conducting a hypothesis test on average, which we will go through very quickly. I would there would be a postulate for theta naught, and I would compute the statistic assuming that postulate to be true. So, you will always conduct the hypothesis testing given that H naught is true. It is a conditional testing that you are doing. You are not doing it unconditional testing. Always the hypothesis testing is conditional. You first fix the null hypothesis. It is like in the court of law, assume that the accused is innocent. Would he or she would have done any of this, right? They say no, that is not likely, right? Then you would come to the conclusion that whatever has happened, whether this person has some weapon at home or carrying some weapon in the hand, is only just by chance. If the defendant lawyer is able to prove that it is only by chance, that it was only by chance that the accused was caught up in all of this, otherwise no, he was very innocent, bola bala, then the judge would have to go by that. But if the prosecutor is able to prove that no, all of this is cannot be by chance, even as the accused is innocent, there was a systematic plan there, and therefore the person deserves to be called as a criminal or culprit and so on. So, that is exactly what is happening in hypothesis testing. You hold on to the null hypothesis, compute the statistic, and then you ask how likely is the observed value given that the null hypothesis is true. As a simple example, suppose R norm claims that the mean is 0, you generate 100 observations, you compute the sample mean, suppose you get minus 2.1 as a sample mean, right, and let us say then you compute the standardized statistic and it turns out to be fairly high. You say that yes, I agree that when the true mean is 0, it is possible that I can get a large value for the statistic, but that probability is very low. Therefore, I would actually refute the null hypothesis rather than actually blaming the realization, saying that it is a low probability realization. That is the basic idea in hypothesis testing. So, remember that no hypothesis test can result in a perfect decision, and therefore, there are two types of errors in hypothesis testing depending on the combination of the truth and the decision. And this table essentially summarizes that. You must have seen this table in the videos as well. Basically, if the truth is that H naught is true and you have failed to reject H naught, then you have made a correct decision, cool. But if you have rejected H naught when it is true, then that is in error, and there is a chance that you will do it. That is what I meant earlier. No hypothesis testing is foolproof, all right. This probability of making this kind of an error is denoted by alpha. This is called type 1 error. H naught is true and you have rejected. On the other hand, H naught could be false. The mean may not be 0 or may not be what you have postulated. Maybe theta is not 0 and you have failed to reject H naught. That is also an error. You should have rejected H naught, correct. That is another error, and the probability of making that type 2 error is denoted by beta. Generally, this alpha and betas are fighting with each other, but do not think that alpha plus beta is 1, that is wrong, all right. And of course, if H naught is false and you have rejected H naught, then it is a correct decision, and the probability of that is naturally 1 minus beta. So, these are the two types of errors that you will encounter in any testing, right, any kind of decision making process. And normally in hypothesis testing, what one needs to specify is one of these two errors. You have to say that conduct a hypothesis test with this level of tolerance. I would like that kind of qualifies the goodness of hypothesis test. So, you have to specify what goodness you want from the test, and typically one specifies alpha, the type 1 error, because I will not go into details, you should sit through the lectures. Calculating type 2 error is a lot more complicated for the user, and it depends on what the actual truth is. Okay. Beta, which is type 2 error, has to be calculated by stating the true truth, not a postulated truth, and it can change with that. So, that is a painful thing. It is a lot easier to specify alpha because you are assuming H naught to be true, therefore, it is fixed, and you are only going to calculate what is the probability of rejecting H naught. So, typical values of alpha are 0.05 or 0.01, and this is the same alpha that appeared in confidence region. Okay. So, just to illustrate quickly, if you are looking at hypothesis testing of a mean, there are 3 possibilities for the alternative hypothesis. One possibility is like this, right. In place of theta you may have mu. The other alternate is that mu is greater than 0, and the third alternative is it is less than 0. So, depending on the alternate, that is why I said you have to be careful in framing the null hypothesis. The region of so called rejection can change, so called critical regions can change. So, you have accordingly a two-tailed test, lower tail test and an upper tail test. Of course, I have written it the other way around here, but anyway. So, if you have an alternate hypothesis of type mu not equal to 0, you run into a two-tailed test. Typically in our modeling and the the whiteness test, we deal with two-tailed tests only, but you should also be comfortable with the lower tailed and upper tailed test. And the alpha depends on the nature of alternate hypothesis. Those red areas that I have indicated, those are probabilities. What you are seeing as curve is the probability distribution of the statistic, the sampling distribution. Okay. This the total area in the red region for the two-tailed test is alpha, and if the distribution is Gaussian, then the areas are distributed symmetrically. So, the idea in hypothesis testing, there are 3 different approaches in hypothesis testing. One is called a critical value approach, where you compare the observed statistic with the critical value. That means what you think is tolerable. If beyond that you say no, it is not possible that H naught is true and I would have obtained this statistic value. And that critical value is is calculated or determined by first specifying alpha. So, for example, in a two-tailed test here, the total area in the red is alpha, and you would read off from the either from the chart or using R, you would figure out this critical value. So, the white region here you can call it as acceptable region. Acceptable means if the statistic falls in that region, you do not reject the null hypothesis. That is a critical value approach. The other is a p-value approach. You look at the probability of obtaining a value more extreme than what you have observed. Okay. Suppose you have, I will go through an example and you understand, but the basic idea is if the probability of obtaining a value higher, when more extreme, let me put say higher would mean always on the right hand side, no, more extreme than what you have observed is very low, then already you are in the extreme region. If the probability of obtaining an extreme a value more extreme than what you have observed is high, then that means you are in a safe region. So, this p value in general, if it is very low, what is very low? In fact, when p value is less than alpha, then the null hypothesis is rejected, because alpha is what you are willing to tolerate of obtaining an extreme value more extreme than what you have observed, and a p value is the observed probability, observed significance level. If that is low, as is said in Professor Ognaike's book, if the p value is low, the null hypothesis must go. Okay, that is simple rhyming statement. And the third approach is a confidence interval approach. In this, in fact, this is the simplest in my opinion. Construct a confidence region, check if the postulated value is in the confidence interval. If it isn't, then you reject the null hypothesis. It is the simplest. You may ask, why you have said earlier that the confidence region can miss out on the truth. Yes, that is the alpha risk. right? Yes, it could have missed out the truth, in which case the null hypothesis gets rejected even though it is true. That is exactly the alpha risk. So, let me just quickly go through an example. Here is a temperature, we are looking at a reactor, and there is an engineer controlling the reactor temperature. He has designed a controller, and the engineer claims that on the average the temperature is at the set point, which is 90 degrees Celsius, let us say, okay, on the average, because at each point it is not possible to maintain. Now, obviously the boss wants this to be tested. So, 720 observations, readings are obtained at a sampling interval of 15 seconds, that does not matter here, sampling interval, and now you want to conduct a hypothesis test of this form. It is a two-tailed test. So, the first step is to compute the statistic, to use the lens, and we use a sample mean. Please remember that if I change the statistic to sample median, then everything changes. The procedure remains the same, but the outcome can change. So, we know that the sample mean follows a Gaussian distribution, in fact standardized one follows a standard Gaussian, and therefore, we choose to work with the standardized statistic y bar minus mu naught by sigma by root n. We assume that sigma is given as 2. What is n here in this example? 720, right, and sigma is, let us say, given to be 2, it is known from some historical data. What is the postulated value? 90. Observed y bar is also given, which is 90.1826. Now, when you look at it as a layman, 90.1826 seems to be very close to 90. You say, chalega boss, I mean, what is the big difference, only 0.1826, can't you ignore? It is a Friday, why are you troubling me, or a Thursday? Friday is anyway already included in the weekend. So, you say 0.1826 on a scale of 90, that does not matter, but that is not how statistics looks at. It looks at this 90.1826 has been, how many observations have gone into that value. The more the observations, then the more you are suspicious that the claim is not correct, because fewer observations can produce more deviations, we have seen that, and also it depends on the variability of the process. If the process is not varying too much, you should not expect too much of a deviation. So, statistics does a very fantastic job of examining the distance between the observed value and the postulated value, and asks if this distance is significant, but not on a subjective basis, on a statistical basis. Okay. That is the basic, another perspective of hypothesis testing. So, all you are now doing is calculating this observed statistic, and all the three approaches give you the same decision, which is that the null hypothesis should be rejected. Why? The critical value at alpha equals 0.05, it is a two-tailed test, is 1.96. We know that the 95% probability interval is 1.96, and the observed statistic is more than that, which means your tolerance itself is 1.96 and the observed statistics is even more. All of this conditioned on the null hypothesis being true. Therefore, you say no, it is not possible. If the null hypothesis were to be true, at least I should have obtained the observed statistic between plus or minus 1.96, that has not happened. Therefore, I reject the null hypothesis. Then the other one is the probability, that is, which is a p-value approach now. The p-value approach looks at the probability of obtaining a value more extreme than that I have observed, and it turns out to be 0.015 in this case, which is less than alpha, and therefore, we reject the null hypothesis. We says that already the observed value is extreme enough, and therefore, I will reject it. Up to what p-values will I tolerate? 0.05, that is what it says. If the probability of obtaining a value more extreme than what I would have I have obtained is greater than 0.05, then I would not have rejected the null hypothesis. And the third approach is a confidence interval, which is I feel the knee test. You simply construct the 100 times 1 minus alpha, this 95% that we talked about, now you are able to reinterpret that in the context of hypothesis testing. So, this 95% confidence interval is now given, and the quick search is for the truth, and you clearly see the interval does not contain the truth. Therefore, the null hypothesis is rejected. Initially, for beginners in hypothesis testing, it is a good idea to go through all these three approaches until you pick your favorite approach, all right. And although each approach gives you the same decision, they have different flavors to them. So, this is the hypothesis testing for you, and this is how you would conduct hypothesis testing for any other parameter. The procedure is the same. You try and work out a couple of examples somewhere from the net or from the video lectures, and you would be more confident. I just conclude the I am just going to skip the conference. I just conclude the part on hypothesis testing by saying here we are able to obtain the sampling distributions, and therefore we are able to compute confidence regions or p value or critical value and so on. In practice, obtaining f of theta hat may be very difficult, as I have already been saying, depending on whether theta hat is coming out of a linear or a nonlinear estimator. If you have a complicated estimation problem and you have to conduct hypothesis testing, then you have to use a modern approach of bootstrapping or surrogate data analysis and so on, where you generate artificial realizations and then you compute either the distribution or the critical value or the confidence region or the p value, one of those three, from your artificial realizations empirically, and then you conduct your hypothesis test. That is what you will see in most of the papers that come out today, because today the computational power is increasing, we can afford to work with nonlinear estimators. Earlier we said nonlinear estimators, we will keep them aside because it is so difficult to compute those, but today we can compute very complicated stuff. So that is why people have now turned to bootstrapping methods. So with this we come to a close on the properties of the estimators. Next week we will start off with estimators, methods of moments, least squares. We have already discussed MLE, and then we will talk about Bayesian. That will conclude the estimation methods. We will take those estimation methods and apply it to modeling, estimating model parameters, estimating autocovariances, power spectral densities and so on, and that will kind of conclude the course. Okay.